Okay. So we talked about optical depth. What it is. It's this is it as a function of wavelength in our atmosphere. This is from Simulations and Observations. This comes from that book, Ultraviolet Spectroscopy, Remote Sensing. That's terrible. It's a shortened title, Remote Sensing the Upper Atmosphere. 1991 Space Sciences Review. It's Bob Meyer's, in grad school we refer to it as the Bible. And he took the whole Space Sciences Reviews for one article on all the observations up to 1991 that had been made in space in the ultraviolet. And all of the theory and all of the simulations to that point. And also looked at future directions for observations and a number of possible observations that could be done. Several of which were followed, including a plasmaspheric observation, which is very difficult to make, but was done by NASA in 10 years after Bob mentioned it in his book. So this shows you a couple things. Shows you, as we talked about, that this is a plot of unit optical depth. That's optical depth is one that's that at that point, if there's a line, that means you've lost 1 over E of your, you've lost E of your incident radiation. So almost a factor of 3. I don't have a laser. I guess I don't need it. Let me see if I need it. Okay, well, it's here in emergency. I mean, you can see for yourselves that up to in the blue spectrum of light, down to right where ozone picks up, all this light gets to the surface. And this is where your sunburn starts. And if you can erode this or move up in the troposphere a little bit, your sunburn could really get back. But that's where it shows the absorption bands that are important here, and O3 is important at that point. So ozone is very important, and you see right away that you absorb a good deal of radiation between 300 and 200 nanometers in the stratosphere. So on the side here, this is altitude, and this sort of the canonical ranges of the atmosphere are shown in this plot. So that's why the stratosphere gets hot, because you're absorbing a lot of radiation. I'll get to this solar spectrum in a minute. You're absorbing a big chunk of the solar spectrum at one particular altitude. The troposphere gets hot because you're absorbing everything else basically on the ground. That's why it gets cold as you go up. You've got a hot plate at the ground and an adiabatic expansion of the atmosphere going up. So there's why the stratosphere gets warm. As you can see, soon after ozone's done, there's not a lot of absorption in the mesosphere. You have to get sort of into the thermosphere already before you get to a plateau where you're absorbing a lot of radiation. And that, I guess I'll jump ahead. And I'm going to come back to this because there's a couple important things here. But the solar spectrum, the flux, the irradiance photons per square centimeter per second per angstrom, just to get your units right, is dropping drastically. So as you know, a black body is going to cut off somewhere around here. The black body for the sun of 5,000 degree surface is going to cut off, well before 250 nanometers. But it keeps going. And why does it keep going? Because there's portions of the sun that are much, much hotter than a black body, and they're emitting radiation for other reasons than just black body radiation. There's all sorts of transitions. You see specific emission lines coming from the sun that you don't really see in the visible. Which goes to me to question, there's some interesting absorption of solar lines in the visible that I didn't know about, that you'd need to figure out, ask a solar physicist what's going on there. I think that's absorption, or is that's self-absorption of solar radiation at the sun. I think this is a measurement of the solar radiation.
That's coming from higher up in the solar atmosphere. Solar atmosphere gets colder.
What, so it drops, I'm sorry, so. I see. I'm looking at these little notches that I've never paid. And so it's emitted in a cold region or it's absorbed. I see. That's interesting. Anyway, there's all this stuff going on. And some of the key ones that are going to give us, so if you look here, where's the baseline here? 10 to the 7th, maybe 10 to the 8th photons, and jumps up to 10 to the 10th. So you have some particularly bright lines that are 100 times brighter than anything else around that may be having an influence in your, that are going to dominate. And for whatever reason, out here, there's the, what's out here, the 10.7 centimeter line. So I think it's on this wall still, but it's probably even farther. And it's somehow related to this 830, to this 304 line and this and 530, several of these EUV emissions. So I wanted to jump forward, I'm going to jump back. So what's the altitude of the ionosphere? I know I've said, but you went through a lab, you looked at the ionosphere in the model. What's the altitude of the F layer? Kind of, where was it? Sorry? 350? Yeah, it can be. It varies, right? Did anyone else see a different number for the altitude besides 350? Varies for a number of reasons. But remember what we talked about was all this business. Here it is. Which equation do I want? The peak ionization rate. Where I was going to do, where's my other slide? I'm going to do ionization. The point I was making here when I took the derivative of this and set it to 0 to get down to this point was that the peak ionization rate is where the optical depth is 1. So this is a plot of two things, the unit optical depth and where for radiation coming straight down, the peak reaction is taking place. If you're driving, this is straight absorption, but we know these reactions are ionizing reactions. And the peak in production of plasma in the ionosphere is not 350 kilometers. It's down here at 150 or 170, 180. So that's where you're producing all that plasma. Which goes to the point of how does it get up there another 150 kilometers, 200 kilometers? That's pretty far to get that plasma up there. And so, well, there's transport processes, and you have to start thinking about transport. So how do you get it there? There's transport. There's diffusion. There's got to be a number way. Well, chemistry, you can store energy in something. I guess that's a list of all the ways that you can modify the ionosphere. But you got to get that plasma up from where you're making it. So diffusion also, in fact, as you make a plasma, as I think you know, some of the laws of charged particle motion, which I think most of you have been exposed to, charged particles will spiral around a magnetic field line. And they'll follow it up and they'll go down. But they don't like to come off of that. The laws of physics do not lend themselves to that particle just walking away from that field line. There's only a couple ways to change how that particle is going to go around that field line. Is change the magnetic field, which is weakening it, so something adiabatic invariant is conserved, so you get a slower gyro motion around the magnetic field, and you strengthen the magnetic field, it can tighten up again. You can interrupt its motion in that orbit. You can have it by collisions. You can cause it to crash into, if there's a particle and it's trying to go around this field line and it stops, it can be caused to bounce and keep moving to different field lines by the impact, by the imparting energy and causing its momentum to change. You can move things along field lines. In fact, that's how you get a lot of the different currents in the upper atmosphere, the Pedersen and Hall currents. A Hall current is in the E cross B direction, where you have a net charge moving in the E cross B direction, not in the electric field direction. If you put an electric field in a wire over here, the charge goes right down the wire in the direction of the electric field. That's what's supposed to happen. In space, you end up doing things and you end up moving things. It's like a bicycle wheel. Things move like in the direction of the cross product. In any case, one way you can get plasma up a field line that's being produced at 150 kilometers, and you want to get a peak up to about 350, is to diffuse it along the field line. You can support that process. There's a thermal diffusion, which can be effective, but what you're going to notice right away is the electrons are lighter than the ions. Electrons are going to take off and try to go, and they're going to take off into the you're producing plasma here. It's diffusing both directions, up and down the field lines. With the plasma that's diffusing down the field line, it's almost over. Like it's it's going the wrong direction. Guys, wrong direction. You're going to you're going to be neutralized back down here in the atmosphere. There's all sorts of products. You're going to turn into, someone had a plot up earlier of all the different molecular products you get in the lower ionosphere. You're going to turn into some molecular ion, and you don't want that. You're not going to last very long at all. We won't even see you later in the day. When it comes night, you're just going to recombine and disappear. The plasma that's diffusing up the field line, now we're talking. The electrons are going to get there before the ions, whatever the ions are. Well, if you have an electron gas over an ion gas, electron gas by its thermal, it has a velocity distribution. It's actually going to start pulling. If you can maintain that velocity distribution, it's going to pull the O plus up with it. So there's actually a net polarization that forms, and what you get is what's called, it's a term if you haven't heard it, and maybe you've seen it, or you'll see it again. Ambipolar diffusion. It's a process that's at least as important, if not more, than thermal diffusion along the field line. Transport. Well, so I think I'm done with that. I wanted to introduce the idea of ambipolar diffusion. You have an electron gas that's trying to take off. It pulls the ions with it. Chemistry we talked about. That's why diffusion can end poorly for anyone that's diffusing down the field line. There's transport. So another way to get up from 150 to 250 or 300 kilometers with your plasma is to push it. And that's great if you're ready to accept the fact that your plasma really just wants to move along the field line. So you can raise, this is sort of a impulsive, like during storm, like we weren't looking at a storm in these cases. We were looking at a quiet time. It was just 2013, equinox of 2013. If it's realistic time, it probably wasn't a lot of geomagnetic activity. But if you come in here with some neutral velocity, you can, well, the first thing you're going to get is charge exchange. If your upper atmosphere is made of atomic oxygen and your ionosphere is made of O+, that's a resonant interaction. Immediately you're able to do charge exchange is obviously available too. That said, there's still momentum stored in the whole reaction by introducing atomic oxygen with a particular velocity. So what you can do is if it's coming from the north or the south and happily we're on a planet with a dipole field around it, let me get my dipole field movie out. I know I have one. Come on. There it is. Dipole planet. There's a story behind this I'll tell you later. But imagine there's wind coming from the north and the south. That's an actual IGRF model. And you can lift plasma if you're pushing it along the field line. You can try to push it back down, but there's not a lot of sources near the equator, right? God, these pens. Nope, I'm voting down the green marker. These are Sharpies. That blue. And I tend to draw all over my own stuff. Ah, there we go. But in any case. So you can have velocity, neutral velocity. It's going to be atomic oxygen, and it's going to be able to lift your ionospheric layer up. But that's sort of an impulsive thing. What you'd really like to be doing is show up with an electric field that's in the right direction. Now, I'm going to draw one that's in the right direction. We saw what did we see earlier? We saw a student presentation on high latitude Joule heating. That is current driven in the high latitude regions. Is that a Hall current or a Pedersen current? It's in the direction of the electric field. So let's go to the northern hemisphere. What you were seeing was an auroral oval. This already looks silly. So the circulation, though, in the high latitudes is generally like this. The magnetic field at high latitudes is generally at the North Pole. The field lines, well, I don't have arrows on mine, but are going down, right? This is the magnetic field in the northern hemisphere. So how do I have plasma circulate? If you didn't even know, if you had no measurement of the potential, you just went and measured how the plasma is moving. So everywhere I look, it's moving perpendicular to the magnetic field. Therefore, and my number one way to move plasma around is in the E cross B drift. And I'm introducing this without deriving it because momentum equation is hugely enormous, and I don't have time to get into it. And I'm not sure it's in any of these books, but who's been introduced to single particle motion in E cross B drift before? So some of us. Velocity, the drift velocity, one of the main ways to cause particles to drift, plasma to drift, is introduce, if it's in a B field, introduce an electric field. And that velocity is E cross B over B squared. And the magnitude of that, just simple. This is one of the simpler things you'll find in space physics. So that you could go back and say, well, I see all this motion of this plasma, I see the electric field. So I see a magnetic field, so where's the electric field? V cross B, V cross B. Wait a minute, V cross V, V. Yeah, so if the sun's over here, all right, let me try this one more time. Keep your right hand out. Velocity crossed with the B field is an electric field in this direction. Right? How am I doing? Dawn to dusk? Yes, this is dawn. Why does this work? Oh. That direction, yes? Is this direction too? Just like that all the way? Here.
Points to decrease of the left.
Please, Mr. High Latitude Ionospheric Physicist, please draw the dawn to dusk electric field correctly. Yeah, there. Okay. It's dawn to dusk in the polar cap.
Yeah.
Okay. That's correct. So everywhere you can do this. You can say, well, I have an electric field here. I have an electric field here. So you can end up drawing potential patterns. If you can draw, easily pick up, if the electric field is this way, this is the change in my potential. The contours of the potential will follow the contours of the flow. Well, that's a good way to move plasma horizontally. But that wasn't my original question. My original question is, how do I drive plasma vertically? Right, so yes, this is the dawn to dusk electric field, cross-cap potential. So in the past, there's been in the past a magnetometer in Greenland. They would go read off what it said, and they would have a relation directly to the cross-cap potential. We said, the magnetometer in Greenland says the cross-cap potential is this. It was never probably off by more than a factor of 2. Okay. So I need this again, though. What about at the equator? If I'm going to diffuse plasma at the equator, I have this environment where at the dip equator, the dip equator is defined by the place where the local magnetic field is horizontal. So there's no way to get plasma up that except by by transporting it with an electric field. Well, what do I need? So I'm going to look at the planet from the sun's point of view. This is dawn and dusk. North Pole. And I'm, for simplicity's sake, going to draw an equator, a magnetic equator, sort of at the geographic equator. And I have field lines going from one hemisphere to the other. Drawn terribly, as usual. I like this one. Okay. So if I want a plasma, if I want to lift a plasma during the daytime, well, I need velocity up. I need E cross B. Nope. I need an eastward electric field, don't I? E cross B gives me up. So I would like to impose an electric field in this direction. If the dipole flips, if the Earth's dipole flips over, we may have aurora, but your daytime ionosphere is going to be completely different. Because all the drift, the electric field that does exist, that does lift the plasma in the daytime, is going to have the opposite effect. I'm really concerned over that dipole flipping. So how do you get that electric field? You can create electric fields. The best way is separating charge. And so I'm still concerned over this electric field being the right direction, but it's right. So the one way to do that, the simplest way is to put some positive charge over here and some negative charge over here. Wouldn't that do it? Electric field starts from positive charge, goes to negative charge, am I right? So how do you get that? Well, of course, it's not as simple as just sprinkle some of the terminators, but if you have a separation of charge, a polarization in the daytime, you can get that effect. You can have a net electric field or a net separation of charge that gives you an overall background change in the electric field. So I will just give it away. It's the neutral wind. The neutral wind at particular altitudes can drag ions better than it drags electrons, and it can create a separation in charge. the puzzle that we've been faced with recently is that this changes drastically from one day to the next, and it seems to be very regional, where we didn't think you could get charge separation changing so quickly across the day side that the field would go up and down across the day side. It seemed like this was, come on guys, the sun is heating the atmosphere, it's stirring things around, and you create this large-scale net, you have this large-scale net effect of a eastward electric field. But it doesn't seem to be the case. So I'm going to talk about that a little bit more, because that's why we built the ICON mission. And it's fun, that some of this is fun because when we went to NASA to talk about the ICON mission and ask them to select it, it was John Gronsfeld who had to make the call. So that's why I was waiting for you guys, because I always like to talk to John because that was his idea to pick ICON to fly it. Okay, so I'm going to go back. Let me go back to these things a little bit more. So really, when we talked about the Chapman layer and it being the ionosphere, the Chapman layer, which I didn't get to derive and I may not even have time to, is really the photoelectron layer. A bunch of photoelectrons are being produced. We say photoelectrons because they're energetic and they just got knocked off of neutral atoms. That layer is feeding the layers above it. I saw earlier, I think in your talk also, you talked about a F3 layer. Is that, you can, if you can move that thing or suppress that thing, that layer of plasma, you can immediately affect the F layer above. I think that's about it. Oh, another thing to note finally before we get off of this is that there's the absorption in the mesosphere goes up to about 100 kilometers. But then it goes down, there's a part of the FUV spectrum that reaches right into the mesosphere all over again. And that can drive a lot of chemistry. So the chemistry in the mesosphere gets really interesting. Realize also that's just 1/3, you have extremely, energetic radiation. Lyman alpha is one of the brightest lines. Lyman alpha is the brightest ultraviolet emission of the sun. Anywhere in the spectrum, it's Lyman alpha is the 1216. It's throughout the universe. It's it's a simple dipole transition of the hydrogen atom. It's super bright, and it gets past that peak, and it's hiding between these two peaks and getting right into the D region. So the D region and the chemistry in the D region has a lot to do with that bright solar Lyman alpha line. That's why the GOES people who have a picture of the sun have a Lyman alpha picture of the sun, because they want that Lyman alpha radiance. Because there's people, NOAA is feeding this information to people who are interested in how much radiation is crashing into the middle of the mesosphere every day and how it varies. A solar flare can change that by 10 to 20% right away. Okay, there's Lyman alpha. You can see it, like I said, I kind of guessed it's the brightest thing. Of course, I'm sure it was, and there it is. This is what the Earth looks like in the ultraviolet, if you go measure it with a spectrometer. It's also, well, I might as well get out the laser. Here's the middle ultraviolet. This is sort of basically just the solar spectrum coming back up, and about with an albedo of about 30%. So we have a pretty low albedo in this range. There's a couple of these regions where we have a positive albedo greater than 1. We put out more light than we get from the sun because of processes that are driven because the excitation mechanism is not like a resonant excitation, but it's a photoelectron excitation. You hit the atmosphere with photoelectrons, you produce light and these other emissions that come out of the Earth that don't come out of the sun. LBH, molecular bands are one of those. There's not a lot of molecular light coming from the sun. Everything's ionized. But we have a lot of radiation coming out and molecular in the form of emissions of, well, N2. Here's one. So in any case, this is where we do a lot of work here, because if you look at the Earth, let's see, what's the fall off? factor 6 fall off in the Earth's radiation. If you look at the Earth, I'm just going to guess that the sun is falling off more than that, from 13 to 7. Factor of 8, factor of 6, 7, 8. It's almost the same. My picture of the universe is falling apart. 8 to 2, 13 to 7, it's about the same. Well, it still works that the ultraviolet Earth is kind of, there's targets in the ultraviolet on the Earth that you might like to know more about that you can't see in the visible because there's too much visible light. But compared to how bright the Earth is in the ultraviolet and the aurora of the Earth, it's kind of almost the same brightness. I'm showing two things here. These are historical. This is history time. I was alive for both of these, but I didn't know anything was going on with Apollo 16. And I did not know when I was in 6th grade that the guys over in Iowa, Lou Frank and company, guys and gals, were building a UV imager that was going to fly around the Earth that I would do my thesis with later. But these images are from that mission, which flew in an elliptical orbit around the Earth, and they flew 2 of them. Someone showed DE2 data. So DE2 was, they had this idea, well, why don't we fly one big satellite with like a 3 to 4 Earth radii altitude, and we'll at the same time, in the same stack, launch a little satellite that samples the environment near Earth, and we'll take pictures of it while we're there. And in fact, sometimes we'll even line up, and we'll be on the same field line. Wow, what a great idea. We stole those ideas for later missions. But well, how are we going to do this? How are we going to build? We don't have CCDs. What are you talking about? What are we going to... This picture was taken with film, and it's a fantastic imager. But they put the film behind a sheet of plastic, and then they focus light from the moon onto a cathode, which electrons would then blast off of it, and then they focus those with a giant magnet to shoot onto the plastic, through the plastic that blocked visible light, but the electrons would go through. And that's the picture that came out of it, off the surface of the moon, which was a pretty neat trick. It showed sort of some of the same things. Aurora, of course, they let this saturate, but it showed the equatorial ionosphere. Equatorial ionosphere showed up in Dynamics Explorer, 2 different pictures. One last piece of historical significance is that the sun is obviously an eclipse image. Like, where's the crescent of the Earth? Here's the sun's over there. Where's the sun? It's on the other side of the Earth. So they waited until the satellite was in eclipse and they took these images. They were not allowed to do this. Like, this was a mission risking, or certainly risked the UV imager. You could have blown it up, which was a photometer, a single field of view. Every single pixel was taken one at a time by this thing. It would integrate, and it would spin, and then they move a little mirror like this, and then it would spin. They had a spinning spacecraft, spinning platform that they had to work with. And the best way to do that was just to build images with this photometer, and every 12 minutes they'd get a picture. We have CCDs now, hooray for CCDs, and we can build stable platforms that have imaging characteristics. In any case, you can also see the upper atmosphere of the Earth in these images. This is the Lyman alpha, and that's Lyman alpha. It is this is, if you had an oxygen camera, it would all be dark here. But they've clearly got their Lyman alpha filter in place, and so you can see the extended atmosphere of the Earth. Something we're still interested in. In fact, here you can see that the change as the Earth is blocking some of the Lyman alpha, that there's a shadowing occurs behind the Earth of that bright emission. Okay. I got to show these images. It's fun to take a movie from space taken by astronauts and tell an astronaut how cool it is. Or have you seen this one? I didn't think you had seen this one. These are images from the space station, and I'm showing this because it's a picture of the ionosphere with a particular recombination emission that comes from the ionosphere in the daytime. And it's this red glow. You can see also there's a little bit of a green glow here as well, which is natural because this is an atomic oxygen emission. This is, like we keep saying, the upper atmosphere is made of atomic oxygen, and if it's going to glow, you're going to see light coming from atomic oxygen that's been excited somehow. In fact, this atomic oxygen it used to be O+, and it's recombined with electrons through a charge exchange interaction with O2. So there's this emission. I want you to watch this. Watch for this. There's this green band and these other emissions. There's a couple different colors here. That green band is an atomic oxygen emission, but that comes from this atomic oxygen that's being excited in the daytime in the mesosphere by these extreme ultraviolet. That's very extreme ultraviolet. Sorry, very far ultraviolet, almost extreme ultraviolet. This is also excited through a mechanism called the Barth Mechanism, which they finally figured out how it got there. It was Charlie Barth, who was a professor here at CU, who launched down how many rockets and how many students worked with Charlie Barth over the years. But that target, that's almost always at 98 kilometers. In fact, when I was giving this slide to John Grunsfeld, trying to sell him on the mission, I said, oh yeah, it's 100 kilometers, and he corrected me. He says, no, they always told me it's 98 kilometers. I think, oh, right, yes, sir. You're right, that's at 98 kilometers, so that's what I tell people ever since. I'm going to show you an orbit goes from here to here of images taken with a Nikon camera with 1 second integration. So every frame has a little bit of you can see how much the spacecraft moves in 1 second. It's 7 kilometers a second, isn't it? I mean, isn't that orbital speed? 7 kilometers a second? Okay.
Sounds right.
Just about right, 7, 8 kilometers a second. So you're going to see things smeared 7, 8 kilometers on the ground. But you're going to see a couple things. You're going to see the Caspian Sea. You're going to see a bunch of gas flares from them flaring off gas from their oil wells. You're going to see the India-Pakistan border show up. It's very, very well lit. And then you're going to see everything on the ground south of there. And you're going to see the ionosphere changing pretty drastically through this orbit. I think I've given everyone the appropriate backing to understand what they're seeing. See, lightning, of course, and here it comes. First of all, notice there's bites out of it. Who took bites out of my ionosphere? Look at that stuff. This is not the smooth ionosphere the CTIP-E model told me I was going to get. No, sir. So, and then does it come back? Oh, good, here it comes back again. I included the long one. Wait, I thought it was over. What is this thing? We have to fly through it again. Until you do, you fly through it again. The space station's about 400 some kilometers, those E layers. So what you'll find also, if you look at your CTIP-E, the peak of the ionosphere could be 350 kilometers, maybe even higher at the equator because all this upward, because all the lifting that's been going on in the day. But what's also happening is that plasma is subsiding. It's getting up there. Why is it in 2 bands? It's because you picked it up. That's fantastic. Good job. But there's no electric field pulling it back down. The next thing it will want to do is be 2 things, gravitationally sedimentate and diffuse down the field lines. So it goes, and when it gets down there to the bottom of those field lines, as it keeps going, it runs back into the more O2. That red line is coming from is caused by an interaction of O+ with O2. These bites are great. This is the first one we saw. I've taken this in IDL, multiplied everything above this line by like a fair exponential factor. There's the next movie. I didn't have to do that. It just came through with the Nikon camera just very nicely. Is anyone interested in atmospheric physics? There's a sprite in this one. Where is it? That's lightning storm. This actually made a GRL article. Oh, I know, if I'm going to see it. Okay, everyone watch for the sprite. I think I saw it, but it went by too quickly. Well, there's a blue jet in the next one, so I'll wait for the next one. There's another shot. I mean, you can look at these all day, right? Different crews have shown up with different camera settings and so forth. Different moonlighting. You can see some more moonlighting now. We have not, I think those other ones are during the full moon. Here comes the ionosphere again. It's got these big chunks out of it again. You can see these curtains that are, there's a blue jet over here. It occurs. It's hard to see. I saw it, I was staring at it at my computer a few minutes ago. Anyway, I think I was getting distracted so badly by looking at lightning that, and of course, those are flares. The other things were fishing boats. You can learn a lot by staring at the Earth from space. That's my takeaway from all this. But let's look at the ionosphere again. This is crossing over Thailand. Here comes the ionosphere, the big layer. Again, the green line is prevalent. There's green at the bottom because you're producing the green emission, and then you fly through it. There should be another band. These are fishing boats using different kind of lights. Fishing for different things, I guess, and here's the second band. So you often see these two bands of plasma around, hanging out at low latitudes. Okay. These are all online too, and you can get the original TIFFs, which are 4,000 by 3,000 or something. So here's the problem. We understand the physics, we understand the winds, we know what should be going on. We understand that actually there's a number of different forcing mechanisms, tides that propagate up from the lower atmosphere that carry winds with them. But still, so we know we can measure the tide, we can go measure it, and still, someone was doing TEC plots where you add up all the electron content overhead in the model. Or you can add up all the electron content overhead in reality. If you put stations out over South and North America and you get all these different views into space to the GPS satellites or other GNSS satellites, you can see that from one day to the next, and now I've taken, this is Christmas of 2011, day before, day after, same time. And you see that the ionosphere, first of all, where's my two bands? I want two bands of plasma at the equator, please. And there's one pile of plasma here. All right, well, maybe on Christmas, nope. In fact, it's got these chunks out of it. Those chunks that you see at nighttime, these bite outs, come from the instability. Here, I'm going to get a 2-second explanation for what's going on. Here's the daytime ionosphere with the E region and an F region. Here's the nighttime ionosphere. It's flat bottom. That can be an unstable situation. And in fact, the plasma, that's the plasma density. It's like there's no plasma on the other side of it, but the plasma density is dropping very rapidly. So it's actually much, in terms of buoyancy, it's lighter. It's a lighter plasma. You can have an interchange instability, or basic, which can, or a, it's the simplest instability. Rayleigh-Taylor instability can form on the bottom of that layer. So what happened? But that's not what's going on in the daytime. In the daytime, it's fine. We're not supposed to get these chunks and bite outs in the daytime ionosphere, but that's what we seem to start seeing in the GPS, in the ground-based GPS. Finally, over here, you can sort of see two bands of plasma. There's one, here's two, but it's still messed up. So you could say, well, geomagnetic activity is driving winds or driving electric fields and disturbing things, and it's just not the case. This is, DST on this time period was like 1 to -3. So we're interested in why the ionosphere is doing this. I submit to you that the color bar is different at this time, but if I brought it up, it would still be a modeled mess and not comparable to the other days very well. So this is a consistent feature of our planet. Has anyone seen the new gold images from gold yet? Has anyone seen a talk? Yes? That is also showing some remarkable nighttime variability that originates in the daytime. The ionosphere is coming down to the night side completely varying in width and brightness quite a bit already before it gets to the nighttime. And we don't know why. So right, if you have a simple picture of a solar-driven wind system in the upper atmosphere and a solar-driven production of plasma, what actually is going on is you have someone turning off, and the Earth planet's rotating, and you look at it on the night side as it comes by and see what happened in the daytime. It's as if someone's turning the knob on and off. You get big pile of plasma comes from the day side, and in a region with very low plasma densities. And then here comes another pile of plasma. It's similar to the, you can say, well, here's a continental region, continent, except it's offset, and then Pacific. So, in fact, it doesn't work out very well to match up against like gravity waves. If you're looking at gravity waves forcing some bulk forcing, it has to be something larger, and we think it's tides. But no one's gone to measure that all at the same time, place and same time. And so that's what we're setting out to do. I think it's break time. Yeah. And, the thing said, don't go off and talk about your mission a whole bunch. That's what it said. So I was on the plane driving Chapman Layer. But I don't know if anyone wants to hear that. We could also get ready for the next thing and see tip. Like I'm imagining that we could have, you have questions, you can introduce the questions and maybe talk about what the lab is going to do next. Okay. 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 That's Icon. 2 years ago. We're on a turnover stand with the solar panels removed. Turn this off.
Make sure it's. Thank you.
Can you make something up? Okay, great. I'm going to shoot over back in there. All right, we'll get started. All right, whenever you're ready.
Okay, I'll get the. Is this thing on? Good. Interested in going to the CCMC. Oh, I found it. How about that? Okay, so I just went fishing at the Heliophysics site for some of the model runs. I see that there's a range of F-107s, some seasonal studies. Oh, I see these are, I don't know. You guys know better already what you're looking at here when you're looking at the seasonal studies. 015, 215, 1215, 1015, I don't understand. I do understand these. So, so instead of going on with more slides and drawing on the board, well, I'm going to draw on the board a little bit, but I think that maybe I'm interested in the CTIPE results in that when I looked at it briefly, there's a million different parameters that you can that are output by that thing, most of which you don't know what they are, right? Like, what is this thing? Am I correct? Did you? I saw some people looking at yes. We're going to find out what these things are. Some of them could be actually interesting. Some of them you don't know, you could probably get right away, just because you haven't been used to the sort of the lingo, is some of the ionospheric parameters. So I think that those would be useful to plot. I want to figure what IP is. We'll figure it out. But the there's only 20 more minutes, guys. I know. 20 more minutes. That's it. So these are all the stations where you used to have ionosondes. They may or may not still have ionosondes. An ionosonde is a simple instrument where you shoot a radio beacon at the ionosphere and you hope that the signal comes back. Well, wait, we don't hope. We look for the signal to come back. If it comes back, then we're below the critical plasma frequency of the ionosphere at that frequency. It came back. If we're above the critical frequency. If it doesn't come back, it went through the ionosphere or was somehow or another absorbed. So an ionosonde simply is that. It's like when you sound for the depth of water or something, you ping it with the sound. Ionosonde is just a play on that word. And everyone now runs a digisonde, which is a digital ionosonde, which creates a code or a pulse, but simply it's not specifically a radar, although it is doing a distance. It is looking for timing. So not only do you measure to see if the signal comes back, but you measure the time that it took from the signal to leave and come back. Is that right? I think that's right. So what you're measuring is mainly the daytime ionosphere, and I've drawn a terrible picture of this thing. And so this is plasma density as a function of, sorry, silly me, altitude and E. There's a couple parameters that you're trying to derive. There's like so many different parameters from the radio, because when you reflecting a wave off of a plasma, you get different modes back. You can excite different modes in the plasma. There's a fast mode and a slow mode and all these X modes. And you end up getting two signals back from the ionosphere. Well, what you're actually, so those ionosondes have a couple different parameters with them, but what you're looking for mainly is NMF2 and HMF2. Those are derived parameters from the radio output of the radiosonde. And that is simply this, the height and the density. I'm just going to say it. Of the F layer. So I know that when we were looking at this before, what would be interesting is to plot the density at the F peak. Is that a plot that's available? Because we were looking at, when I was asked a question, what altitude we're looking at? We're looking at a fixed altitude. Well, only a few times is the F peak going to be at that fixed altitude in that map. What I'm really interested in, that's why we switched to TEC, because then I don't have to ask the question, well, where's the F peak? If you could, TEC may be fine, but if you can get NMF2 everywhere in a global map, then that tells you how big the peak in the F layer is versus adding the plasmasphere in. The plasmasphere is a big component of this thing, and so that was another question I had when we were looking at plots, looking at these differences in latitudes. Like, well, if it's the ionosphere, it's one thing, but if they're adding the plasmasphere in there, I don't know those physics. I'm not ready to answer a question for the ionosphere without knowing that it's separate from the plasmasphere. and TEC specifically contains the plasmasphere. Total electron content. If you add up all the plasma from the ground to when you run out of plasma, or you get to your GPS satellite, that's the TEC measurements we see are total electron content between you and a GPS satellite. There's not much more after that we care about at all. It's not geoeffective. I couldn't get to the list of weird parameters in this thing. Ionosphere, thermosphere. So immediately a question, oh, well, maybe they cut out the plasmasphere. Maybe that TEC actually is only ionospheric, but I don't know.
So I think this just visualizes the low altitude and visualizes the upper altitude.
Right. Rho. What? Okay, so rho is the H. Oh my goodness. Okay. So I'm going to get into this. Rho is the density. H is the scale height. The neutral temperature, the number of electrons, Vn ln Vn latitude. That's usually the zonal and meridional velocities, and I don't know what IP is. What is that? Is that the IP that's part of the? I see Vn is attached to an IP. Pressure.
So I guess you can plot.
So if I'm looking for velocities in a model like this, I'm looking for the zonal in the north. Zonal is the east-west, meridional is the north-south, and a vertical wind. We call it vertical wind. So if it's going through if there's a vertical wind through your plasma, through your pressure level, then that's a transport, and you get to count that, and you can go plot it. I assume that in these super quiet times, I don't know why they say IP. Isopressure. Thank you. So you have iso contours, single pressure levels, and if you have so the other thing you can have is you can have the pressure level moving as well, which is a different thing to think about, and you could watch that change over time, but I'm not sure they're showing that. P joule, P solar, and P radiative. Pressure, not pressure. Production? No, I don't know what those P's are. Particularly that I see a W joule. Ion drifts. You can get the motion of the ions. Something you should be able to go to the equator and show an ion drift at say 250 kilometers, 250 kilometers. Plot around the equator. Ion drift should be upward in the daytime and downward at night. That's the. Wait a minute. I need a vertical ion drift. That's just latitude and longitude. I have to keep looking. I don't see it. Maybe this is, no. This is very interesting. But, so there's NMF2 and HMF2. I'm going to search into the parameters. I'm going to try to understand. There must be some documentation somewhere.
I'm sure it looked it up at one point in time and picked out the one that applied.
Yeah. Yeah, well, in the corner. Someone was already plotting the different molecular ions. That's great.
Yeah.
Solar cycle of O to N2, If you're interested in the total neutral density, you just add N2 and just add these three up. If it'll do that, and you can get a total neutral density as a function of the solar cycle. But NMF2 and HMF2, I'm interested. TC above 140 kilometers, I don't know why they do that. But this does cut out the plasma sphere based upon just the title of this page. These are Pedersen and Hall conductivities. These are coming from the auroral region. If anyone wants to go up north and search out, see what the aurora is doing, you could do an altitude profile of these across the pole. If you do a pole-to-pole cut of those are height-integrated Pedersen and Hall conductivities, I think. So they should. You don't have to probably fish down to some altitude to get to them. It should be a height-integrated. So it'd be interesting to see that from pole to pole. There's just a million things you can do with this model. I didn't see vertical ion drift though, so I'm questioning my. I'm sure this model's got something like that, but I can't find it. Are there electric fields? What are these E1400, E140, and E300 theta and lambda? Are these electric fields, theta and lambda, at 2 different altitudes? I have no idea what those things are. Okay, we need to go look for that. I need the manual. I need the owner's manual for this thing. In any case, I think people are given sort of open season here to go make plots of variations of this set through the solar cycle. You have NMF2 and HMF2 in here. But I'm sort of interested in all this stuff, so I'm happy to. If we start the lab, then maybe we'll. I'm interested in this, and I'm going to walk around and see what people are plotting.
So we've got a couple of choices. We have a longer break scheduled now, which we could take 15, 20 minutes and then come back and finish up the lab with, especially with Tom's guidance and pushing us in different directions. Or we can just start the lab. Break. Break. Give me thumbs up or thumbs down. Break. No break. Thumbs up. Break. Break.
Good.
And we've got.
Oh, there's.